Namaskar, welcome back. So this was our last slide where we were talking about that how field mapping should be conducted, and as I mentioned that 2 decades back, mostly we used to use the theodolite or maybe the ebony level to generate the topographic profiles, and we used to use this type of post. Okay, and then one person will say, okay, fine, it is at what height we are, and then we will keep recording that. Now, one thing here is, so now we will see that what new technique we are using. Of course, the methodology remains the same. We need to have the relative height of any landform, tectonic landform in particularly, and the photograph at the bottom shows you the fault scarp. Okay. Now, important point here is that the dots which I was showing here. So, this is a scarp, and then the dash line which shows is the trace of the fault on ground. Okay. So, whenever there is a displacement, this topography will develop. Okay. So, if I put a section here, so for example, you have, so this surface and this surface was same at before the earthquake. Okay. So, you have sort of a flat surface here, and then because of the displacement this has gone up. Okay. So, this has moved up, and that what you see, and after the erosion that we will learn in coming lectures. Okay. So, after the erosion this portion has been eroded, and then what you see right now is something like this topography. Okay. So, this is basically what we call the fault scarp, and as I told that we will also discuss when we are discussing uh, the fault systems and all that, we will talk about that. Now, the most important part is because the portion which is like this has gone up. Okay, this has moved up along the fault here. Okay. So, this portion will show sort of a deformation, and this is, so this portion is deformed, and this side will be undeformed. And we should open the trench, because this is important part when we will be talking about the trenching and all that. So, this whole portion has to be excavated. Okay. Maybe you can start from somewhere here and then go down like this, but this portion has to be excavated, and for that we need to have a complete topographic profile of the undeformed portion and deformed portion. Okay. So, we need to have, this is deformed portion and this is undeformed. So, trench will be something like, if I put the trench here, then it will be something like you need to open the section like this. Okay. You can go up to this part if the scarp is smaller in terms of the height, otherwise you need to open just from the base here if the scarp is higher. Okay. So, depending on the height we have to take call, because if greater the height, more events have occurred along that fault. Okay. So, this part keeping in mind the topographic profile has to be taken covering larger portion across the scarp, covering the undeformed and deformed region. Okay. And that what is been shown here, the dots which shows is our the probable locations or the points where we should record the elevation and all that. So, this is what has been done. Okay. Now, why this is important, because we need to also have the understanding of the height, the change in the height what we see from the base. Okay. So, as I told that if there are multiple events which have occurred on this particular fault, then you will have greater height of the scarp. Okay. And that will suggest a sort of an cumulative height which it acquired during different events or multiple events. Okay. And then we need to talk about the height. So, this is basically we are talking about the relative height actually there. Okay. Of course, if you are using high resolution GPS antennas and receivers, then you will be able to have the height with respect to the mean sea level also, that is elevation, but otherwise we are mostly interested in the relative height. So, this will give you the height. Okay. So, you get the height here, okay, and that also helps us in talking about that how many events have occurred on this fault and what was the average elevation change during each earthquake. Okay. Of course, there will be and sort of if the fault is sitting here, then we will also talk about the slip, that how much portion, okay, has moved during one single event. Okay. That is in terms of the height. Okay. The slip is along the fault, but the height will be gained. Okay. Further, if you move, then we started using total stations. Okay. And total station gave us very good measurements, precise high resolution measurements, and we can take multiple points using this total station. And total station usually has been used using one because it will transmit the laser beam, and you have a prism, and that intersection or the connectivity of the prism and the laser beam will help you in recording the height or the points where the person is standing with the prism. Okay. So, then the total so first was as I told that it was a very old method we were using, then later on we came up with the total stations. Okay. So, we also used, as I told, the theodolite and all that, but there was limitation with this. Okay. The limitation was like if we this is the area where we did with the old technique and all that. Okay. So, I will just share that part with you, and this is the outlet of Beas river in Punjab Himalaya, the foothill zones of Punjab Himalaya. So, what we did was that we can have the topography. This is very high topography, but we did that mapping here. Okay. And then this is the portion where what I was talking about. This is the trench we opened up. Okay. So, this portion is your trench. So, we open up the trench across the scarp. Okay. Now, coming to this part here, the second fault scarp we have. So, here also you can see this part is like down and this portion is up. Okay. So, we did topographic profiling using the theodolite auto level, we can say that, and again you can see we have the calibrated measured post, and that person moved from the base to the elevated portion here. Okay. So, but the limitation what I was talking about is that this unit or the instrument will not move, because we need to measure. For example, if you have the beam which you are triggering, and the instrument should also move up and down, okay, and right and left. That has to be then, because you are not fixed that you have to take one line, but in this we have to go in the straight line. Of course, we can move laterally along this horizon, but we won't be able to move up and down. Okay. Because the elevation if changes, then you will have to focus and change the triggering of your laser beam from the main station. Okay. So, that limitation was there, and because of this we were forced to move our station again and again. So, once we have done until the limit it looks, okay, the post. So, we did up to this, then again we fixed up our station here, and then again we took the profile. So, multiple times we were forced to change the station. This is the your base station actually. This is your base station. Now, this again you need to have lot of corrections and all that. So, later this was been resolved by the technological development and all that. So, we use the robotic total station. Now, this total station what we have, and many of us who are in this field or maybe using for the topographic mapping, they mostly use the robotic station. Okay. Now, robotic station has an advantage that it will lock your prism and that wherever you move it will automatically try to connect itself. So, it is sort of in what we call a single person can do this mapping. Okay. Not two people are required, because in previous one you need at least two persons, because one at the station and another moving with the calibrated post. Okay. So, here that problem was resolved, and with another point, because total station it needs to have the connectivity with the prism. Okay. So, it need to have that sort of an sight. Now, suppose this is getting hidden somewhere behind the object, or you have a thick vegetation which is not allowing to focus or connect your prism. In that case you have issues. Okay. You will not be able to take that point. Okay. Then we have another solution to add it to this was using the integrated system. Okay. So, where we can put the receiver on the top, okay, that is your antenna, GPS antenna on the top, and that can also seamlessly work, and the person can move with the prism as well as the another receiver. Okay. So, that one can do. Further, even if you are not having this total station, then you can do the mapping in real time kinematic mode. Okay. And even you can do post processing kinematic or integrated total station you can do. Okay. So, in this RTK and PPK, what one can do is you can have a base set up with one receiver, okay, and another one is been mounted on the calibrated again the post, okay, and that you can keep carrying and taking the point. Okay. Another important point here is that you need not to stop and stay to collect the point of your desired area, okay, but you can keep moving it. You can set up the timing that at how much interval you need, it's 5 second or 1 second, or you can decide that. You can feed it in the instrument, and that will allow you to take the points or the readings in continuous mode. Okay. So, you can just keep moving, it will keep taking the points. So, you in that sense you will have more number of data points, and that will resolve your sort of a redundancy of errors, as well as they will also help in having high resolution topographic maps. Okay. So, this exercise mostly we do in different terrains, and mostly we are comfortable with this because it is quite effective. However, this profile what you see here, this is from Kangra Valley, and so we have a total station here, and then we move because this line of sight was very clear. We usually tried to set up the station. Before that we survey the area, we move around and then try to find out the best line of sight where there is no hindrance. Okay. So, that site will be used for fixing your station, and then you move. Okay. So, that will make you ease to have more number of points. Okay. So, that usually is one basic part which everyone should do. Okay. So, this topographic profile we collected, and it is not very like the elevation is just 1.2 meters, but it is very precise, okay, the elevation. Then as I told that along with the total station and integrated GPS, you can have multiple points. Okay. Now, since this area was quite open, you can see the top photograph, and the line of sight was very clear. So, we use integrated system here, and that helped us in preparing what we call the digital elevation model. This is exactly the DEM, okay. Which clearly shows when it is processed and plotted. You can see the scarp here with different color, because the darker one is showing the higher ground. This is higher one, and then you have this sort of an feature which we see. So, this portion is this here, and this one is right here. Okay. And the topographic variation, it goes like this. Okay. There is no sort of an information of the topographic change here, but there was a fault here which we identified. Now, this we wanted to do because we wanted to have an precise data on this offset. Okay. And what is terrace risers we will discuss later on, but there was an elevation change, and this was right lateral strike slip fault. So, the portions here moved like this. Okay. So, the right block moved towards us, hence we call this as a right lateral fault run somewhere over here. So, to have such an high resolution data, we collected multiple points, and then it was been processed. Okay. Now, again the other part is that we can also have. So, one part is that we did topographic mapping. Now, things will be like where to put trench. Okay. Because as we have been discussing right from the beginning, that we need to have the section, because the evidence or the signature of past displacement which is associated, or the slip which is associated with earthquake caused by earthquake, is been preserved on surface and in sediment succession. So, precisely identifying the fault, we can have other techniques or the methodology one can use, okay, to see subsurface. And the best way is that what we have experienced, okay, is that the ground penetrating radar. So, ground penetrating radar usually uses the electromagnetic wave transmission and receipt also. Okay. It receives back the signals, and depending on the change in the dielectric properties of the material, you will see the contrast. Okay. So, I will show couple of profiles here how it looks like. Okay. Now, here this area again in Punjab region, and the area is over here where we did the total station profiling or topographic profiling we did, plus we did GPR, and we did also trenching. So, complete study what is been required for any paleoseismic investigation. So, this is the outlet of BS here. BS flows like this, and the scarp is here. Now, it was like easy for us because it is well exposed, not much of the vegetation cover, but then also there was limitations with us, and that was from the villagers. Okay. So, in our country we have Sarpanch. So, Sarpanch told that what you are going to do here. So, we told that we need to open the trench. So, we need to use the JCB or the digging machine, and then we need to remove the material, and that how big we will do that also we explain. The concern of the villagers were that there is a water pipeline which passes through this area. And as per the what we have learned from the previous slide, okay, that at the, for example, if we put this here, okay, then we have, so this is your scarp, and fault plane is in section. So, this part is your sectional view, and this is your scarp here. So, what you see here is looking from down, looking up, and then you have an house here. Okay. So, this is a house here which is setting. Okay. Now, as per the previous discussion we had, the fault trace would be somewhere here, or it would be somewhere over here. Okay. So, that will be slight variation, but precisely it will be in this area. Now, the concern was that there is a pipeline which also goes through here, okay, and the arrows which have been marked is the probable location of the fault trace, okay, with an understanding and experience that, okay, fine, this is the scarp and the fault plane must be over there. Okay. So, we did GPR over here, and that helped us in identifying the particular site. So, this was like topographic profile also you take and all that. This part I have already discussed before, that we will be generating anaglyphs and using stereo photographs, and you can have this on the digital platform on your PC, okay, that you can use, and then you can identify the based on the elevation change and all that, the fault scarps and traces of the fault. Okay. So, geophysical method basically will come to the GPR profile, and I will show that also. So, geophysical methods have been used in terrestrial paleoseismology in 3 ways: as a reconnaissance technique to define shallow stratigraphy and structure, and this is the structure, we are not talking about the civil structure, but this structure is your geological structures, okay, in the fault zone area, or even we can identify the liquefaction. Now, liquefaction we will, I have briefly mentioned somewhere in the beginning, but we can have detailed discussion. We have a separate lecture on this. Okay. So, the idea behind this is, or why we are using this technique, is that we need to identify precise trench location. Okay. And as towards the end, probably we have couple of slides which talks about that how different the trench techniques or the methods are being used in different countries. Okay. We will come to that also, but in India mostly few groups work on this, but we mostly we have like this standard methodology, like sort of an SOP we have developed for our work, that we will definitely do ground penetrating radar studies. Okay. And this helped us in reducing the digging area, okay, because it costs a lot. It is dangerous in that sense, because trench can collapse, plus you cannot keep digging across the fault scarp. Okay. So, you need to have very precise, because you need to go deeper at the place where you have the fault. Okay. So, for example, if we were talking about here, so we need to go deeper at this location, because that will yield us or give us the information of more number of events preserved in the stratigraphy. So, this is one part, okay, that we do a reconnaissance, and to locate the optimum site for further trenching or drilling if you want to do. Okay. Then for tracing faults to generate to greater depth, then that can be reached by trenching. Okay. Because you will not be able to do unless and until you go for a very wide trench, because as you move deeper, the stability of the walls, okay, which are been open, will reduce, okay, and that can collapse. So, for that we need to have a smaller area which usually we open. We normally in Himalayas in particularly we go up to the depth of 3 to 5 meters, okay, not more than that, because of the loose sediments and chances of collapse is higher. But with this technique, GPR technique, you will be able to trace the fault plane up to the greater depth, okay, beyond what you can dig. Okay. So, that is another advantage. The third is for detecting buried faults that have no surface expression. So, as we were talking about that, we will see the scarp, okay, and then we will open up the trench, but some places this has been eroded. Okay. So, fault is somewhere here, like this in 3 dimension if you put. Okay. So, fault is here in this sense, okay, but in some locations you will just see a flat topography, but fault still exists. Okay. And in this case we will see, so we have all flat over here. Okay. So, in this case the GPR also helps us in identifying, and this is exactly what we were been able to do in the Kangra Valley, where I was showing that in one portion we were not having any trace, but there was a trace of the fault, and GPR helped us in taking that. Okay. So, these are the 3 important points for the geophysical in the sense overall. Okay, geophysical technique we can do. You can go up greater depth, you can identify, narrow down your trenching site and all that. So, we will stop here and we will continue with more details on geophysical technique in next lecture. Thank you so much. Namaskar.